Hey guys, hello everyone. Welcome to UNACADEMY once again. So here we are in next another very important video where we are solving all the important CSIRNet question of 26th November 2020. So there were two papers in the November 2020 and we are going to solve both of them, all the organic session. So yes, first we are going to solve questions of 26th November paper and I have taken all the important questions, not only the name reaction but other important questions like pericyclic, like organic reagents, reaction mechanism, intermediates, everything I've taken over here. All right. And I hope that this video is going to help you really, really well in your next exam preparation, which is very close. So yes, guys, don't forget to like and subscribe to the channel. Right, let's begin quickly. You have to stop for the question and try it by your own. It may take you like 2 minutes, but then still try it by yourself and then only see the solution. Okay. I'm just going to give you all the solution, but you have to honestly stop and quickly do the question by yourself. Okay, chalo, let's begin. So first question, guys, the following transformation involves a series of. So this question, guys, it's actually a little tricky and it might take you a little bit of time, but if you have done these kind of question, it will be very obvious. What are the options? It could be electrocyclic ring opening or closing reaction, cycloaddition, cycloreversion, sigmatropic rearrangement, chalotropic reaction, or elimination reaction. So what is it? Basically, let's look at it at the next page. Now, when you are trying out 4 plus 2 cycloaddition, see, you can see that there is a one double bond, another double bond over here. So you might be tempted to do 4 plus 2 cycloaddition, but then you, after doing the reaction, you see that you can never get this product from 4 plus 2 cycloaddition. How are you going to approach? You are going to first move the electron density over here, and then you are going to draw this molecule. All right, one carbonyl, a negative charge, and a positive over here on the nitrogen. So what does it become? This becomes something like the azomethane ylide or you know, just 1,3 dipolar species if you want to call it. Okay, now you do the addition to the cyclooctadiene. Yes, now you are doing the dipolar 1,3 dipolar addition to this single alkene. You are going to guys get something like this, and in this question, even if I'm telling you the answer, you have to visualize a lot, isn't it? So yes, see, I have this carbon over here, this nitrogen over here, and instead of writing inside, I'm writing this outside. This nitrogen has a pH still, and still there is this carbonyl as well as the oxygen over here. I just hope that you understand. I have just inverted this nitrogen like this. Why? Because now I can clearly see that if there is heat given over here, what can I do if there is heat provided? I can just use this nitrogen lone pair to push this bond from here, and the bond falls up like this. Okay, and onto the nitrogen, you are going to get elimination. All right. Yes, just not this bond. Remove not this one. The bond is going to fall over here, and this bond falls over here, right? You are going to get elimination of carbon dioxide followed by something like this. So you have used the double bond. Now you have used the double bond. There is a negative charge on this nitrogen, positive on this nitrogen once again. What does it look like? See, if you want to write it like this, then also it's okay. Or if you want to consider this possibility, just like the before one, that having a nitrogen-nitrogen double bond and having a negative charge on this carbon, it is actually the same thing, resonance structure. So you have once again, by the elimination of carbon dioxide from here, see, let me just erase this bond so that you can understand better this thing. Yes, now it's good. So once again, you have generated the 1,3 dipolar compound that is going to give you the cycloaddition once again, and that will result into the exact same molecule which is written over here. I'm not going to draw it over again. You just have to imagine that these two carbons are getting connected and these two nitrogens. See, one nitrogen is connected and one carbon. Look over here. One nitrogen and one carbon. Yes, to the cyclooctadiene system. Both of these four carbons are free. So it's like the molecule is bending around this molecule, right? Looks like the cyclooctadiene is bending around this particular molecule by two consecutive 1,3 dipolar addition reactions. Okay, this is going to give you exactly this molecule. Okay, guys, try it out. Very, very, very important question. So what just happened? Cycloaddition happened. Which cycloaddition? 1,3 dipolar addition and cycloreversion to eliminate CO2. And then one more cycloaddition happened. But the answer is option number 2 only. Why? Because we are not doing electrocyclic, not sigmatropic. Kelotropic addition is not happening when you add something like SO2. Okay, when you're adding SO2 or you're adding a carbene like this, then it classifies as kelotropic reaction, not 1,3 dipolar addition. So B is the correct answer for this question, guys. Let's quickly move onwards. Next question. Major product formed in the following reaction is. So many people were confused in this question, guys. In the presence of a base, you are having so many carbonyls. You have 1, 2, 3, 4, 5 membered ring possibility. You have 1, 2, 3, 4, 5, 6 membered ring possibility from this side, and 1, 2, 3, 4, 5, 6 membered ring. So you have 5 and 6 membered ring possibility. Although you can get a 5 membered ring much faster than a 6 membered ring, but in the product over here, what are you going to get? You're still getting the 6 membered ring. Why is that so? Yes, why is that so? Because guys, when you are, let's say, drawing the enolate, let's say I am removing, this is your CH3. Let's say I'm removing a proton from here. Alright, I have removed the proton from here. This is my enolate. So in order for the reaction to happen, just like we draw the 6 membered Traxler transition state, so that is, something like this. I've already drawn it, but see over here what is given. I need the carbonyl to be over here, and I need the enolate, O minus, to be over here in this way, right? And there is some metal which is chelating to both of these, either sodium or lithium, whichever, right? So if I just roughly consider, although the chelating possibility is higher for lithium and very less for sodium, but still considering a stable possibility, considering this 6 member transition state, you have to see that for this to happen, for this attack to happen in this way, you require a chain over here, which is actually long enough. Yes, for the molecule to arrange in this way, the chain must be long enough, and that is why you are forming a 6 member ring and not a 5 member ring because of this chain. If the chain length is small, the molecule will not be able to arrange like this, right? So that is why you are going to favor the 6 member ring formation in the intramolecular aldol condensation. Okay, it is intramolecular aldol. Alright, so B is the correct answer. Moving onwards to this question, yes guys, in the following transformation enantiomerically pure lactone A provides. So what is this reaction? Yes, this is a name reaction. If you write this molecule properly, it would be really good to answer. How properly? Like this. See, there's one carbon, which is one CH2 group, which is below the plane, and this is a 7 member ring. It's better if you write this ring in this way. Alright, and there is this one CH2 group over here, which is below. Why do I say it? Because now you will be able to easily see the role of the reagent. Or if you want to invert and bring the CH2 above, that will be great. Okay, and just understand that these all bonds are below the plane when the CH2 is above. Okay, so let's check what is happening. Catalytic palladium tetraphosphine. So absolutely guys, when you have such a possibility that you are having the catalytic palladium, see this bond is below. So, first of all, the platinum or the palladium, if they are going to connect to this double bond, they are going to coordinate to the double bond, and then the bond opens from here, so that you can get the acetate is free, and you are going to get a pi allyl complex. Now the question is, since the acetate was considered to be below the plane, the pH is going to, sorry, the palladium is going to attack from above the plane. Okay, it is going to attach to this pi allyl complex from above the plane. Now, what is given in the question? Malonate has to attack. So this malonate ester, this one, it has to attack. From where it is going to attack? From this side or from this side? Absolutely the least hindered side, which is right over here. But above or below, it is going to attack from below only. Alright, so if the malonate ester, let's write the molecule as it is. Let's say I'm writing COH. So if the malonate ester attacks from here, it is going to be something like this: CO2Me, CO2Me over here. Both of these are going to be below the plane, and the palladium can get removed. This is nothing but the Suji-Trost reaction, guys, where first of all, in the presence of palladium, you form a pi allyl complex followed by the nucleophilic addition. Okay, in this way. So after the nucleophilic addition, it only rests to a double bond. There will be no conjugation to this carbon anymore, only the double bond, right? So what is the question asking? Enantiomerically pure lactone A. So yes, guys, when the lactone is pure, then the attack is only taking place from below the plane, isn't it? This attack was from below the plane. This is also from below the plane. That is not a problem. You are only getting a syn diastereomer of B, which is racemic. Alright, why is it racemic? You are getting a syn diastereomer, that's okay. That is both of these groups. This is also below, and when it attacks, see, when this malonate attacks, that is also below. Why are you getting enantiomer, racemic mixture? How is it possible? See, there are two possibilities to this pi allyl complex. One attack is taking place from over here, and the other could take place from over here. That the malonate could attack from here as well, and that is going to give you two mirror images. See, from below the plane, because here also they will end up in the 1-3 position, and here also 1-2-3 position. So they are going to actually look like this. Yes, let's say this is one of the products in which both of them are below the plane. The other product is going to look like this, because both of them will end up on 1-3 position to each other by both the attacks. Try the attacks by yourself, guys. It is very, very important. So they are going to be like this. Okay, that is why racemic mixture, two different attacks are possible. Syn diastereomer means that both the groups are on the same side. So this is the correct answer. Moving onwards, guys, next question. The major product formed in the following transformation is. Now this is a very easy and direct question, guys. Just by looking at the dienone system in the presence of acid, you know it is Nazarov cyclization. This Nazarov cyclization, what happens in the presence of any Lewis acid? Here FeCl3 is given. One of the bond is going to open up. Let's say this bond is going to open up like this, and this bond attacks. So it is, guys, it is a 4n pi electron thermal conrotatory cyclization, electrocyclization reaction. Yes. And if both the hydrogens are trans to each other on conrotatory motion, they are going to end up trans. So that is, the ring cyclizes in this way, and the hydrogens are going to be both trans to each other like this. Okay, very, very important, guys. So you have opened this from here, OFeCl3. There is a positive charge, and there is SiMe3 over here. Alright, so guys, there's one more thing that you can do. You can just shift this pi bond from here to here. Why? Because on the other side there is a positive charge, so it will happily take away the pi bond, and this side will happily take away the positive charge. Why? In this way. Why is that so? Because the Cl minus, which will become free from here, is going to attack over silicon, and silicon happily loses its electron density to the molecule, becoming a pi bond like this. And I'm finally writing the product after the aqueous workup. So this is going to be our final product where the hydrogen is still below. Alright, so why do we get this product, guys? Yes. Why only silicon removing from here? Why not this hydrogen? Because silicon is first of all more electropositive than the hydrogen. Second thing is we have a beta silicon effect. What is the beta silicon effect? That whenever there is a carbocation present on the beta carbon to silicon, it will be stabilized by hyperconjugation like this. Okay, so this is basically hyperconjugation, sharing the sigma bond, right? And that is why the answer is option number D. Nazarov cyclization, very well. Let's move onwards to next question. In the given transformation, the intermediate A and the major product B are. So once again, very easy, very easy, guys. Just going to take a little bit of your time, right? So yes, there is no base over here, and the PHCHO does not have a acidic proton to remove. What can it do then? In the presence of CuCl, you see N double bond CH CO2 ET. This is what you see, guys. What is going to happen in the presence of CuCl? It is going to eliminate nitrogen minus N2, and you are going to get a carbene like this. Okay, I think I've done this in the next slide. Yes. So, alright, you got a carbene over here by the elimination of this nitrogen minus N2. And yes, what just happened? Either you form the carbene first or you do this reaction first, it is the same thing. Let's say we have formed the carbene, CHCO2. What will happen? The only nucleophile which is present in the system is this. It is the only nucleophile which is present, guys, nothing else. So ये carbene, it is going to attack over the carbene, and it is going to end up having a positive charge on oxygen and negative charge on the CH. Okay, this is what you get. Nothing else, no other nucleophile present. So absolutely, this is the species that you get. What is this? 1,3 dipolar species. So there are two questions which got asked from pericyclic, both from 1,3 dipolar species, right? Yes, and after that, there is one more equivalent of aldehyde, benzaldehyde, which is present. It was given in the question only, and you can write it down in this way. Yeah. All right. So this is what you have. All right. Let's check if we have connected the right way. You have pH and two oxygens connected to it. Absolutely. This is correct. So A is our answer. This one. This is our correct answer. Why is this wrong? Because the regioselectivity is incorrect in this. That is why. This is the correct regioselectivity, guys. Two equivalent of the aldehyde you are taking with this molecule. Why is this regio correct, guys? Because you can see obviously negative charge is going to attack on the more electropositive carbon. Alright, chalo, let's move onwards. Let's do another good question, number 85. The major product A and B formed in the following transformation are. So you see over here what's happening. There is a sodium hydride in both the cases. The molecules look same only, just that there is a nitrogen and there is a sulfur. Is that going to make a difference? Let's see. So yes, very interesting question, guys. Sodium hydride is going to remove the proton from both of these. Alright, let's say remove the proton from here, remove one of the protons from here, got a negative charge, very fine. Whose negative charge is going to attack on whom? That is the question. Okay, so sulfur, as you are I know you are guessing this thing and you are absolutely correct. Sulfur is going to give you Michael addition in this way. One, two, three, four, five. Five-member ring formation, that is going to give you a ring like this. Okay, which further going to become like this. Alright. What about nitrogen? Nitrogen is going to do the direct addition. Yes, absolutely. Why is the difference? The difference is of the hard and soft interaction. Sulfur is soft and that is why it attacks the carbon, which is basically a little bit far away from this oxygen. Nitrogen is a hard base or hard nucleophile. That is why it is going to directly attack on the carbon which is connected to oxygen directly. So hard soft interaction, and that is why you are having two different products. So once again, D is the correct answer. CH2O is nothing, it is just HCHO, formaldehyde. Sometimes formalin is also given, which is the polymer of formaldehyde in the presence of acid, so it's the same thing. CSA is camphor sulfonic acid, so that's just a good acid you have to know. What is that good acid going to do? So whenever we see HCHO or any other aldehyde and we see nitrogen, we are just going to quickly protonate this aldehyde and we are going to quickly make the iminium ion or the imine. Obviously, this proton is going to be removed from here, and that is how you get the iminium ion. Okay, this is what we have got. So through the iminium ion, we might want to do a 3,3 sigma tropic rearrangement, even if the heat is not given. Right, the bonds are going to go all over here. Yes, and this is what you have got. Still the iminium ion, still a positive charge on nitrogen. But this reaction looks like an intramolecular manic reaction. The OH bond is going to fall over here, and this is your enol. Enol is going to attack over here, followed by the imine is going to react. So, one and how many? One, two, three, four, five, six, seven. Seven-membered ring forms. Seven-membered ketone is going to form. Yes, absolutely. Just one carbon extra I have written down, so just make it something like this. Yes. Right. So this is going to be your answer. I have missed on one pH group also, which is going to come over here. So as such, there is no stereochemistry or nothing is asked. Only the reaction is asked. What could be the proper reaction in this scenario? That is asked. So it is iminium ion formation, P3 sigma tropic, followed by manic reaction. And guys, this combination has been so frequently asked. Sometimes they ask you that what is the order of reaction for this mechanism, iminium ion formation, P3 sigma tropic manic reaction. Here they have just given you the reactant and the reagent important. Next, another repeated question. Major product formed in the following reaction sequences. So yes, what do you see over here? You are having substituted, three substituted pyridine. Okay. So this substituted pyridine, guys, looks like there will be ortholithiation, isn't it? Because whenever you are having butyl lithium, The lithium gets chelated with the oxygen and removes a proton which is more acidic. Now there's always this competition. Who is going to be more acidic? This proton or this or this? Right. So absolutely guys, this proton is least acidic as compared to this one as compared to this one. Why? Because it is closest to the oxygen and usually the C4 position is anyways electron deficient. So that is why the fourth proton is going to be the most electron deficient. Acha, let the molecule be as it is. So the negative charge is now going to attack the iodine. It is not going to attack the carbon, it will attack the iodine so that the alkene eliminates and you are going to get the iodopyridine. 4-iodopyridine. See, look at this. 4-iodopyridine. This is wrong. This is correct. Absolutely wrong. It is not going to attack on CH2. It is going to attack on the iodide, right? So this is also wrong. ये तो wrong है ही. Why? Because this proton is less acidic than this proton. ये बहुत ज़्यादा acidic है. More acidic. Okay, so that's why your answer is option number B. Alright guys, next question. Look at this question, very important. The structure of A in the following reaction is. Now, in this reaction, it is actually very simple, but you might get confused because here the reactant is asked, not the product. So it might confuse you a little bit, but just follow what has to be followed. Okay. So in this type of question, you have to try out the options for one by one. Otherwise, it is not possible. So let's try out option number A. Okay, and then let's try to do all these steps on this molecule. What can be done, guys? Yes, what can be done over here? See, first of all, I have taken this molecule in the presence of light. We can try out a 2+2 cycloaddition and we'll see if it doesn't work out, not a problem. So we have done 2+2 cycloaddition in the concerted mechanism or radical, it is going to be the same, going to give you the same thing. Second step is ozonization and Me2S. Right, so ozonization, first of all, we are going to break this alkene over here, and after breaking the alkene you get this molecule. You are going to get both of these forms oxidized. All right, last step is NaOET ETOH. That is a base. You are having a ethoxide base. Guys, whenever you get two carbonyls and a base, you absolutely are going to do aldol reaction. So aldol is so basic, but it is asked everywhere. Looks like this. So this is one hydrogen over here which could be lost. You are going to get this one enolate, O minus, one carbonyl. So the enolate is going to fall over here and the bond opens up. You're going to get 1, 2, 3, 4, 5 membered ring. Alright, there's this oxygen over here. After one carbon, this oxygen is okay. And there becomes an OH. You have a 5-membered ring. And this carbon is this one. You are getting a carbonyl over here. After the even CB elimination, you have a base, and through the even CB elimination, you are going to get this final molecule. So is it the same molecule that we have in our product? Let's check. One side you are having the double bond. Absolutely, looks like yes, absolutely this is the same molecule, which means that the reactant is right over here. You can also check out what you will get through the same mechanism, 2+2 cycloaddition followed by the ozonization and everything. You can try out for all the other ones, but अगर मुझे answer मिल गया है, then I'm happy. A is the correct answer. Okay, चलो. The major product formed in the following reaction is. What can you do? It's alpha beta unsaturated carbonyl, and then it is CH2, एक carbon छोड़ के acetate, one carbon छोड़ के SiMe3 guys, yes, you have palladium. When you have palladium and when you have such a possibility of formation of pi allyl complex, you are absolutely going to do so. So this is your pi allyl complex which is going to form after the elimination of acetate. Yes, there is your palladium which is going to connect to the pi allyl complex. And then what happens guys? See, there is a positive charge over here. It's a strange molecule, but you are going to get the gist of it. So, yes, let's say in the presence of you are having PD, right? I've written PD over here. It's palladium, right? So, in the presence of palladium, the bond is going to leave. You're going to get a pi allyl complex. Basically, if you want to show it as a complex, it's okay because mechanism में तो हमें क्या चाहिए? We need to write it properly in the mechanism, right? So this is your pi allyl complex with the palladium acetate, and then when the acetate is free, it can attack over silicon also, so that the electron density falls this carbon, falls up on this carbon, and what does it give you? Let's say it gives us cycloaddition. How? ये देखो, becomes a 1,3 dipolar species. This one. Yes, right? It becomes one positive, one double bond over here, one negative. Isn't it? Becomes more like a 1,3 dipolar species which is going to attack onto this system. Right? And you are going to get alright, one double bond here as it is. So this is your molecule that you have got, and both of the hydrogen and the CH3 they are going to be on the same side since it is a concerted mechanism. So both the methyl and the hydrogen will be on the same side. They cannot be trans guys because here also they were on the same side. Okay, very beautiful reaction. First of all, pi allyl complex formation, the acetate attacking over silicon to leave the electron density, and you are going to just do the cycloaddition to give you this molecule, option number A. Alright, very, very important. Let's look at this one. The correct sequence of reaction involved in the following transformation is. So this molecule looks very tricky, but you just have to follow simple reaction, aldol and Michael, and you just have to see the sequence. So let's say we try out aldol first, because if you don't do aldol, you won't have alpha beta unsaturated carbonyl, तो Michael कहाँ से होगा? So that's why you need to multiply this with 2 and you need to do the aldol reaction first. Let's see. If we do the aldol reaction, I am directly writing the products. Okay, you try this out, you're going to get the same thing. You get this alpha beta unsaturated ketone. So first you have to do aldol. Michael nahi hoga first mein, because now you can do Michael. How? By making this enolate O minus, by making this enolate attack on the conjugated alkene system. Now you can do it, no problem. Okay, so first you'll do aldol, then you will do Michael. So this is also wrong. Two aldol back to back, not possible, right? So first you do aldol and then Michael, and then let's see what happens. Yes, this is what you have. Alright, this is what you have. Now what I'll do is I'll just directly write this molecule as a carbonyl, and then in the presence of the same base I will try to remove a proton from here. Why from here? Because you see both the ends of the carbonyl are locked. So one end is already forming a bond with this ring, the other end must also form a bond with this. That's why I'm using it up. So this attacks over here, and there is the bond over here connected to one more ring. So this is one more ring. There is an OH and there is this bond and there is this carbonyl once again. Alright, So you absolutely get this thing. I just hope that you do. All right, and it is basically going to give you the same molecule right after the reaction. See, what do you have? One, two, three, four, five, six. One, two, three, four, five, six. All right, so you get a similar product. One side there is this, the other side there is this. So aldol condensation, Michael addition, aldol reaction. Number 91, right? The major products formed in the following reaction is. So you see over here, this is not a very difficult question. It's absolutely easy, right? LD, what's going to happen in the presence of LDA? You just have one acidic proton which is going to be lost in this way, and it is going to give you a carbanion, or let's say enolate. Okay, let's say I'm writing, you're getting a carbanion over here, directly writing the carbanion. Where is it going to attack? It's going to attack the CH2 pH and Br is going to eliminate. But the question is from which side the pH2, the CH2 is going to add. It is going to add from below the plane because the phenyl is a bulkier group and it is present above the plane. So the alkylation of the enolate will take place from below. This one could be correct. However, you are not going to remove this proton. Absolutely wrong. Above the plane is absolutely wrong. Yes, this is also wrong, right? So your answer is option number A only. From below the plane, pH to pH is going to attack. Next, very important, awesome question. The major product formed in the following reaction is. See, it's a little bit different mechanism. You just have to use your brains over here. Very different mechanism. So PPH3 is used as a nucleophile over here. What is PbSOTF? OTF is a good leaving group. Alright, OTF is a good leaving group and TBS is tertiary butyl dimethylsilyl. Like that only. It's a silyl, trialkyl silyl group. Okay, so it's going to be attacked by the oxygen and OTF is going to leave so that you get OTBS and the enolate is locked over here. PPH3 is also locked having a positive charge. Yes, keep that in mind. It is going to have a positive charge now. What happens next? N-butyl lithium is going to remove a proton from where? Don't do this mistake of removing this proton from here. Absolutely wrong. It is going to remove a more acidic proton from here. And it is going to give you a carbanion from here. What does it give you? It gives you ylide. Yes, absolutely. It gives us ylide. So this ylide is going to undergo a reaction with butanol. What does the butanol look like? Let's say I'm just writing RCHO because R could be the number of carbons. So butanol is going to attack and give you a betaine intermediate, and this is no less than a Wittig reaction now. Yes, isn't it? It is exactly your Wittig reaction. All right. So you're going to get a double bond on this side, having the R group. That is your butanol chain basically. So you are not going to do this mistake of addition onto this carbon. It is absolutely wrong. You are going to add it over here. And after the TBAF you are getting, what is the F minus going to do? It is a fluoride source. It is going to attack over silicon and the bond is going to open up in this way. After the bond opens up in this way, after the bond opens up, you are going to also get a proton, two protons on this carbon. Alright, so this is the chain that you have, two protons over here and the alpha beta unsaturated carbonyl, which is the more stable format. So B is the correct answer for this question. Now guys, another beautiful, very important question. This is the major product formed in the following reaction. It might look like that it's a very big molecule. You might get scared of it. But look at this, honestly, really easy. See, excess of TMSCl, triethylamine. So triethylamine is going to just pick out this enolate proton over here. You are going to absolutely get an enolate. Let me just write the enolate over here. Minus charge. Excess of TMSCl is going to lock the enolate. O minus it would be, so it is going to just make it OTMS. All right, and you already have a enolate, right? Now, who is going to add alkylation of the enolate, or what is going to add to the enolate? What is the positive species? That is the most important thing, guys. You would normally say that this molecule, this CH2Cl, should be attacked. Yes, isn't it? You will normally say that the CH2Cl should be attacked. And do we have it in the reaction? Yes, we do. Everything else is correct, is it? Yes, it is. So it could attack over CH2Cl so that the bond falls over nitrogen, or it could also attack over this fluoride, which is a small electrophile, and the bond can also fall over nitrogen, right? So it attacks over the F and you get this product D. This is the major product and it's a very important reaction, all of you. Very, very simple. Nitrogen is having a positive charge. It is tri-substituted, which means that the fluorine has to give its electron density and the fluorine will be attacked rather than fluorine attacking. How important. Okay, very, very important over here. Next question is the correct statement for the following transformation is. So guys, I have also made you do this question before. We are getting two different products based on the enamine that forms. That is, if you are forming this kind of an enamine, okay, that there is NH2 and the carbonyl is going to, attach to it. Let's say if you are having two different enamine formations, okay, in this way. If you're having two different enamine information, one from here, what's going to happen? It is going to cyclize in this way. Alright, leaving behind two methyl groups. And if you have another type of enamine, that is, if you have, let's say, the double bond is over here. F. So you have the ethyl group present over here. Yes, absolutely. So the new ring is going to form in this way. So that is why you're getting two different products, P and Q. This is going to lead to P and this is going to lead to Q. Alright, different type of enamines going to give you different kind of cyclization. Right, but when is which enamine going to form? So it is very, very important. This Q is preferentially formed via condition B. H2SO4 ACOH under thermodynamic control, right? So absolutely it is in the presence of acid more substituted enamine form. This is a tri-substituted enamine, right? It is going to form in the presence of acid, right? And this is a less substituted one will form in the presence of base. All right, so acid catalyzed is under the thermodynamic control or equilibrium control, that is, right? 96 answer is option number D. Very, very, very important. Okay. Yes. Last question. The major product formed in the following reaction sequence is question number 98. So what do you do over here, guys? CH3P double bond CH CO2 So you have a CHO which is 3 over here. All right, no problem. Let's add it to the CHO. You have CH3 double bond OET, which means you are going to have the uh, you know this is CHCO. Alright, so this is one hydrogen, this is another hydrogen, this is COO. Yes, you're going to have the trans alkene, right? Like this. Alright, because of the elide which is formed. Now, can we do some other reaction? Let's say in the presence of heat, can we do a simple reaction? What kind of a reaction? Let's see what is possible. Guys, it is so obvious that now if the oxygen has to attack on this ester and do the coumarin type ring formation, this is a coumarin type ring formation, isn't it? Yes, but for doing that, this oxygen must be free, and there is this whole group over here. What is the reaction? Para-Claisen rearrangement. Absolutely awesome question. Para-Claisen, that is this whole group is going to go. So how does it go, guys? First it will go to the ortho by 3,3 sigma tropic, and on the ortho the connectivity will be from the tertiary carbon, and once again it does rearrangement, it goes to the para, connectivity will be as it is. So that is why I can just directly send this part of the molecule to para, to the oxygen. Okay, and I'm directly doing the tautomerism so that you get the benzene ring directly. And now you have this CO2 over here, so which is going to basically give you the ring formation, coumarin type ring formation. Although it is trans, but in the presence of a little bit of acid, it can form cis also, and it will do the coumarin ring formation, which is going to end up like this. All right, very, very important. So we are doing, first of all, Wittig reaction, and secondly, we are doing heat in the presence of this elide, which means we are doing the Para-Claisen followed by the coumarin type ring formation over here, intramolecular ring formation. Answer is option number D. Okay. Yes. Why is all this written, guys? ये देखो, in the options you see all this is written because it is this group is going to be like this in the ortho position, not para. Para के अंदर ये वैसे का वैसा same हो जाएगा. So both of these are wrong. Chalo guys, I just hope that you enjoyed and understood plenty of stuff. Now we have discussed plenty of questions from the 26th November paper. We will do the same for the December paper also. And you have to tell me in the comment section what are you liking, what do you want more on this channel, what do you want me to elaborate on, anything that you want to know, okay? And also don't forget to subscribe and like the channel, okay? I'll see you very, very soon. Bye everyone. Take care.